Welcome back. We're back for video 4 from Unit 1. Last video, we began our studies with sequences and looked at different ways that we could generate terms from sequences, both recursively and by an nth term rule. So we're going to continue. We'll branch out and look at some geometric sequences. It's going to be jolly good fun. Let me go ahead and share the PowerPoint with you. All right, from the current slide. Come on now. There we go. If you remember from last video, when we tried to find a 6,000th term, if we were doing it recursively, it was kind of problematic because to find term 6,000, you needed to know term 5,999. And you got the idea. To know that term, you needed to know 5,009. It got to be a pain. If you wanted the 1,000th term on an nth term example, you guessed it, my friends, we don't need any previous knowledge of other terms. We would simply plug 1,000 into the formula, and we would in fact find the term that we were requested. So in that sense, I've always kind of believed nth term definitions are a little more flexible, maybe a little more user-friendly than maybe a recursive look. All right, new challenge. This time they're going to give us some terms. They're going to ask us to go ahead and find a rule to try to write an nth term rule that would generate those terms. Now, in the past, this has been a challenge for some of my students. They haven't enjoyed this as much as what we just did on example 2. So what I'd ask you to do first of all is look at that sequence of numbers critically and see what kind of information you can draw. And the first thing I think that maybe we ought to see is it looks like there's a common difference of 2. So, all right, well, maybe I can make use of that somehow. Maybe somehow that gets incorporated in. So what I'm going to ask you to do is draw that observation. And you've already found that. It looks like those numbers are 2 apart. So, when we get something on our paper, the worst thing we can do is stare at a blank paper. So maybe we write our potential, our prospective nth term as a sub n equals 2n. You say, well, that's what I know. I saw the 2. I'm going to go ahead and begin. I'm going to write 2n because I know the 2 seems to be significant. Now, we could be having a good day, and that might be correct. Sadly, most times it won't be correct. We're going to have to do something to that form that we've advocated and somehow make it create the terms that are listed for you on the screen, namely the 6 and the 8 and the 10 and the 12. So, all right, what I propose we do is test our rule out. You ready? If we go ahead and put in a 1, will we get 6? Because we know the first term is 6. Bummer for we put in 1 and it looks like we get, for our potential, we get a 2. So we ain't got 6. So we got to somehow edit. We got to do something to our 2n because it's not getting us the terms that we wish. So, the first thing I'd ask you is, well, what do you have to do to a 2 if you were hoping to get to a 6? And somebody in the room is going to say, well, shoot, you could add 4. All right, well, then that might be our next modification. So the notion of trying something to see if it works, to see if it sets what we want in motion is not a bad strategy, even for advanced solvers like us. So maybe that's what we'll do. We'll modify our general form over there that says a sub n equals 2n, and maybe we'll change it to, all right, well, shoot, if I add 4, that might get it. So here comes our edit. You guessed it, we're going to try adding 4. So now our potential nth term has been modified. It's no longer just 2n. It's now 2n plus 4. And the challenge again is, will this work? Can we put 1 in and get 6? Well, shoot, we kind of already know that. So the kicker is, can we put 2 in to try to generate the second term and get a result of 8? Can we put 3 in to try to generate the third term and get a result of 10? All right, so that's what you would have to do next. You would subsequently put in the numbers n is 1, n is 2, n is 3, n is 4, n is 5, and see if that general form that we have staring at us from the middle of that screen is going to be good enough to generate responses of 6, 8, 10, 12, and 14. And I kind of think it will, but I'm going to leave that up to you to check. All right, one for you to try, and I'm just going to sit here and drink some coffee and look handsome. Well, you say, well, what would I do? Well, if you tried it the same way as last time, looks like if you're looking at this thing critically, here's we're adding 4 each time. So maybe we would just write a sub n equals 4n. and then have to do some kind of adjustment because sadly 4 times 1 doesn't get you -6, right? 4 times 1 gets you 4, and to get that -6 you would have to diminish by 10. So the correct answer for an nth term here is 4n minus 10. One of the most famous sequences in all of mathematics is attributed to Fibonacci. Your author presents it in a recursive look. First 2 terms are both 1. Starting at term 3, terms are created by adding the 2 previous terms. So to add 1 and 1, you will create term 3, which is then 2. To create term 4, you will add terms 2 and 3. So if you add 1 and 2, you will get 3. You see the 5 out there, that's gotten by adding the 2 previous terms, the 2 and the 3. So that's the recursive look as it relates to Fibonacci, one of the most famous sequences in all of mathematics. Contrasting arithmetic with geometric as we move farther into our study of sequences, geometrics don't add to get from term to term, they multiply to get from term to term. We'll call that fixed multiplier the common ratio. And in a similar way, when we discussed arithmetic, we talked about adding and or subtracting. For geometrics, it's multiplying and or dividing as you proceed from one term to the next. But again, the kicker is the number that's being multiplied or divided has to remain constant. It can't change. For those of you who remember some algebra, this is a good place for exponents to sneak in. So in a real sense, geometrics tend to look a little more cluttered because you can see exponents showing up. And you probably do remember that a to the nth power is just a whole bunch of a's being multiplied together. In fact, there would be n factors of a representing a to the nth. That is important that we understand that's different than n times a. Right, that's a different set of mathematics completely. This is a set of n factors, all of which are a being multiplied together. All right, for those of you who want to show off, a to the 0 is 1 if we agree that a isn't 0. We've all heard math teachers, including yours truly, say anything to the 0 power is 1. That's almost true, but it's not true because 0 to the 0th power behaves very oddly. It's a really lovely calculus term, and as such, it's outside of the range for this particular class. All right, my friends, ends video 4 for Unit 1. We'll be back shortly with video 5. See you then.